Hi, this is Kycia, and I'm going to be presenting DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise. This is for Professor Anthony Breetzman's class in Data Quality and Web Text Mining, CS 02625, due December 7th, 2022. For the agenda, first I'm going to go through an introduction. I'm going to, in general, covering clustering algorithms and types. Then DBSCAN density-based clustering. I'm going to have a DBSCAN clustering process example. And Tony recommended this, but I'm going to talk about k-means too and compare it to DBSCAN. So I'm going to talk about k-means partition-based clustering, which we talked about a lot in class too in the past this semester. Also, k-means, going to go through a clustering process example. Differences between k-means and DBSCAN clustering. DBSCAN clustering advantages, DBSCAN clustering disadvantages, and then I have Jupyter Notebook examples, both for DBSCAN and for k-means. I have copies of the HTML output in these PowerPoint slides, but I also submitted for both of them Jupyter Notebooks that can be run so you can actually, see the code execute and see the output. Finally, I'm going to have a DBSCAN summary at the end, and I'm going to cite the sources I used from both the internet and some YouTube videos that I watched and also used for the two examples. Introduction. Clustering, first of all, is an unsupervised learning method that divides the data points into a quantity of specific batches or groups such that the data points in the same groups have similar properties and data points in different groups have different properties in some sense. DBSCAN, which again is density-based spatial clustering of applications with noise, is a density-based, non-parametric clustering algorithm. DBSCAN groups together points that are closely packed together with many nearby neighbors. DBSCAN marks as outliers points that lie alone in low density regions. DBSCAN is a very common clustering algorithm as k-means, and both of them are two of the most popular cluster algorithms in unsupervised machine learning. In 1996, DBSCAN was proposed by Martin Ester, Hans-Peter Kringle, George Sander, and I'll try to say this name at the end as Rory Zhu. I'm not sure, but just to talk about these people a little bit further. Martin Ester, born in 1958, he's a Canadian-German full professor of computer science at Simon Fraser University. His research focuses on researcher data mining and machine learning. Next, we have Hans-Peter Kringle, born in October of 1948. He's a German computer scientist and professor at the Ludwig Maximilian University of Munich and leading the database systems group in the Department of Computer Science. George Sander, and on these last two, I couldn't find birth dates, so I don't have them here, but he's a professor of computing science at the University of Alberta. His areas of research focus on data mining and database systems. And finally, Rory Zhu is a professor of information science at the University of Arkansas at Little Rock. His research interests are causal AI, transfer learning, lifelong metric learning, active learning, density-based clustering, and network clustering. Okay, and these four individuals also issued a 6-page white paper in 1996 detailing DBSCAN, and here's the information about it, but I included a PDF of this white paper in the PowerPoint slides, and it's also readily available on the internet if you search for it, so it's very easy to find, but it's here for anybody who wants to read it in the PowerPoint slides. Okay, clustering algorithm and types. As I said before, clustering is an unsupervised machine learning algorithm that divides data into meaningful subgroups called clusters. The subgroups are chosen such that the intra-cluster differences are minimized and the inter-cluster differences are maximized. The definition of a cluster depends on the application. There are many clustering algorithms. So in general, these algorithms can be classified into 4 categories as follows. The first is density-based, which is the focus of this presentation. DBSCAN is a good example of that. For grid-based clustering, CLIQUE is another application. And then we have hierarchy-based, and we talked about that a lot in class this semester. But some examples there are single, complete, and average linkage. And you'll see later on you can also do top-down or agglomerative or bottom-up. And finally, we have partitioning-based clustering. And a good example of that is k-means. So first we're going to talk about, in general, density-based clustering algorithms. And they assume that clusters are dense regions in space and separated by regions of lower density. A dense cluster is a region which is densely connected. The density of the points in that region is greater than a minimum. Since these algorithms that span clusters based on dense connectivity, they can find clusters of arbitrary shapes. And you can see some examples here, especially in the center there. Some of the algorithms such as k-means, I think, might have a harder time with that. So again, DBSCAN is an example of density-based clustering algorithm. Next, we'll talk about grid-based clustering. The entire data set is overlaid by a regular hypergrid. The clusters are then formed by combining dense cells. It's also considered as a variant of density-based clustering. And CLIQUE is a grid-based clustering algorithm, and you can see an example here below. Next, we have hierarchical clustering algorithms. Seek to build a hierarchy of clusters. They start with some initial clusters and gradually converge to the solution. And there's 2 approaches here, agglomerative top-down. Each point has its own cluster, and clusters are gradually built by combining points, and then divisive or bottom-up. All points belong to one cluster, and this cluster is gradually broken into smaller clusters. And then we have partitioning-based clustering. Divide the data set into initial K clusters, and depending how you do that, it's going to affect your outcome. And it'll really improve the clustering quality based on the objective function. K-means is an example of a partitioning-based clustering algorithm, and the objective function in K-means is sum squared error. Partitioning-based algorithms are sensitive to initialization, and you can see an example with 6 iterations below. Okay, DBSCAN density-based clustering. The DBSCAN algorithm finds dense areas and it spans these recursively to 5 dense, arbitrary shaped clusters. 2 main parameters to DBSCAN are E, epsilon, And that's basically when you have a core point that you start with, that's the distance you go out from the center of that core point, kind of put a circle around it, to that distance or radius. And that's where you're going to look for other points. And then you define minimum points, okay? And minimum points is how many points you need to have to get a cluster. So epsilon defines the radius of the neighborhood region, and minimum points defines the minimum number of points that should be contained with the neighborhood. So if you have a core point with an epsilon of a set value, you draw the circle around it, and you set minimum points to a value. The number of points, which includes the core points, has to add up to minimum points, or a cluster is not going to be created. Also, DBSCAN is a concept of noise, so it works well even with noisy data sets. Classification of data points, and you can see examples here below. Noise points in red, border points in blue, and core point in black, or core points. And this is example with minimum points set to 4, and on the bottom circle there, with the red dot, they show epsilon, and again, that's the distance from a point, going out where you look for other points. So core point, A, selected point is considered a core point if it has at least a minimum number of points, again, minimum points, within its epsilon neighborhood, including itself. Black spots in the figure below are core points that have at least minimum points equals 4 in their immediate vicinity. Okay, next we have border points. A border point is a chosen point that is the vicinity of a core point, but is not itself a core point. Blue spots are marked as border points in the figure below. If we have a border point, it signifies that the point is close to or on the edge of a dense zone. And finally, we have noise points. Okay, a selected point that is neither a core point nor a boundary point. This means these points are outliers that are not associated with a dense cluster. And again, in the figure below, you see the red dots, and those are marked as noise. DBSCAN algorithm steps. Okay, first you want to find all the neighboring points within epsilon, that distance I talked about, and identify the core points or visited with more than minimum point neighbors. For each core point, if it is not already assigned to a cluster, create a new cluster. Then find recursively all its density connected points and assign them to the same cluster as the core point. So a point A and B are said to be density connected if there exists a point C which has enough points in its neighbors, and both the points A and B are within epsilon distance. So this is a chaining process. So if B is the neighbor of C, C is the neighbor of D, and D is the neighbor of E, which in turn is neighbor of A implies that B is the neighbor of A. So you iterate through the remaining unvisited points in the data set, and those points that do not belong to any cluster that you create are considered noise. Here's over on the right, you can again see the core point and just how the DBSCAN works. So epsilon neighborhood, or neighborhood of epsilon, there is the set of all points within the distance set by epsilon. Core point, a point that has at least minimum points, including itself, points within its n neighborhood of epsilon. Direct density reachable, a point Q is directly density reachable from point P if P is a core point and Q is part of the set of neighborhood of epsilon. Density reachable, 2 points are DR if there's a chain of DDR points that link these 2 points. A border point, points that are DDR but not a core point. And finally, noise, points that do not belong to any points neighborhood of epsilon. So they're kind of out by themselves, and they don't cluster with any other points. Okay, over on the right here, we have a pseudocode, a serial algorithm for DBSCAN. And this algorithm proceeds by arbitrarily picking up a point in the data set until all points have been visited. If there are at least minimum points within the radius of epsilon to the point, we then consider all these points to be part of the same cluster. The clusters are then expanded by recursively repeating the neighborhood calculation for each neighboring point. The complexity of this algorithm is O n squared, where n is the number of points, and the spatial indexing of the complexity is O n log n. Okay, next we have a DBSCAN parallel algorithm on the right. This is from 2011, and it was presented a disjoint set based on DBSCAN, and the algorithm's called DBSCAN. The algorithm uses a disjoint set data structure. Initially, all points belong to a signal. You start with your data points in A. They belong to a singleton tree in B. And then if 2 points belong to the same cluster, their trees are merged, and you can see the intermediate trees. And this process is repeated until all clusters have been found. You can see the final trees. And here's some pseudocode on the right, parallel clustering, DSD, DBSCAN. And this one uses the REMS algorithm, 1976, to construct the disjoint set tree structure. And it defines the complexity. The cluster trees are constructed without any specific order, and the DBSCAN algorithm is suitable for parallel implementation. And I didn't include slides on this, but I did find some things on the internet that I read about where, you could get a bunch of computers, the computer itself and other computers working in parallel to solve these kind of problems faster in parallel. Okay, next I've got some slides that I really liked. I found these on the internet, and they just help describe and visualize epsilon and the minimum number of points. There's just it's good visual here. So first, this green dot here, consider a core point, and then the line going to the circle is the radius, or epsilon. And epsilon is simply a distance that you set. The dotted line is representation of that distance. You can think of it like a radius from a data point that broadcasts out in all directions, forming a perimeter around that data point. Okay, minimum points. The green circle in the center there is the randomly selected core or starting point. The gray circles are the data points which fall within epsilon of the starting point and are known as core points. Minimum points is the minimum number of core points, including the starting point, that must exist for a cluster to be formed. So in this case, it looks like we have 7 points in that circle. So if minimum points was more than 7, might have a problem forming a cluster there. So that's an important parameter. And here we show glowing clusters. 3 new data points are found. These are called the border points. Border points can't directly reach the starting point, but can be chained together to reach the starting point indirectly. Okay, next, finalizing a cluster. When no more data points can be reached, the cluster is finalized. So all blue points here now represent the completed cluster. And white points right here represent points that haven't been clustered yet. Okay, and then you continue the iterative process, to form other clusters. So we restart the process by randomly selecting a new starting point. That's the one in green here. And then, go epsilon out from those points and look for other points, which they did there in the circle. And here's where we finish clustering. Now, when clustering is complete, it may look something like this with multiple clusters being formed. Now, something important just to see here again about the red cluster, it could only be formed, that red cluster, if the minimum points was set to 3 or less. So if minimum points was set to 4 or more, that second cluster wouldn't form, and those, I guess, would remain as noise points. So here we have a DBSCAN clustering process that I found, example that I found on YouTube, and you can see here on the top right in blue, the first cluster being formed. Okay, now on the bottom left, the second cluster is being formed in green. Okay, the next cluster is on the bottom right in red, and you can see there on the left around the green, you see 3 points that weren't marked green. Those are noise points. And we have 1 noise point down with the red. And now we're doing the last cluster in the upper left in, looks kind of like light blue. But this will finish up, and then the points that aren't marked, okay, they're the noise points. They were actually marked in black here. And that's the end of that demo. Okay, now we're going to have a couple slides on k-means partitioning-based clustering. Tony recommended that I talk about this too and compare it to DBSCAN. But the k-means algorithm is an iterative algorithm that tries to partition the data set into k predefined, distinct, non-overlapping subgroups or clusters where each data point belongs to only one group. K-means tries to make the intra-cluster data points as similar as possible while keeping the clusters as different far as possible. K-means assigns data points to the cluster such that the sum of the square distance between the data points and the cluster's centroid, or arithmetic mean of all the data points that belong to the cluster, is at a minimum. The less variation within clusters, the more homogeneous or similar the data points are within the same cluster. Okay, the k-means algorithm steps. First, you specify the number of clusters k, and by doing that, you can definitely affect the outcome, how many clusters you pick. You initialize the centroids by first shuffling the data set and then randomly selecting k data points for the centroids without replacement. Then you keep iterating until there's no change to the centroids. Assignment of the data points to the clusters isn't changing. Then you compute the sum of the square distances between the data points and all the centroids. You assign each data point to the closest clustered centroid, and you compute the centroids for the clusters by taking the average of the data points that belong to each cluster. And here's a k-means clustering process example, again, that I found on YouTube. So we'll run that. And you can see your data, initialize the centroid positions, and we picked four clusters. You assign labels to the data, and shows a formula. And now it's repeating the process, and you want to do that until you get the same result twice. So it's going to continue to run. And you can see the new centroids. And you're going to repeat steps 2 and 3 until you have convergence. And the centroids just moved again. and moved again. And that's our final result. And you can see 4 clusters with the big points as the centroids. Differences between k-means and DBSCAN clustering. K-means clustering. Clusters are formed are close to being spherical or convex in shape and must have the same feature size. K-means clustering is sensitive to the number of clusters specified when you start. K-means clustering is more efficient for large data sets. It does not work well with outliers and noisy data sets, which DBSCAN clustering does. In the domain of anomaly detection, the algorithm causes problems as anomalous points will be assigned to the same cluster as normal data points. K-means clustering only requires one parameter, the number of clusters, K. Varying densities of the data points doesn't affect K-means clustering algorithm. For DBSCAN clustering, clusters formed are arbitrary in shape and may not have the same feature size. The number of clusters need not be specified. DBSCAN clustering cannot efficiently handle high-dimensional data sets. DBSCAN clustering efficiently handles outliers and noisy data sets, which K-means does not. DBSCAN algorithm, on the other hand, locates regions of high density that are separated by one another by regions of low density. And it requires, as we discussed before, 2 parameters. Epsilon, or the distance from the core point, which can also be thought of a radius for a circle around the core point, and the minimum number of points. R determines a chosen radius, or the radius, such that it includes enough points within it, then it's a dense area. M, or minimum points, determines the minimum number of data points required in a neighborhood to be defined as a cluster. DBSCAN clustering does not work very well for sparse data sets or for data points with varying density. DBSCAN clustering advantages. First, DBSCAN algorithm is robust to outliers or noise points, as we've said before. DBSCAN is great at separating high-density clusters from low-density clusters. Unlike k-means, DBSCAN does not require the number of clusters to be specified prior to execution. DBSCAN supports non-globular structures as well. Some of the disadvantages of DBSCAN clustering. DBSCAN does not work well for clusters of varying density. Although it clusters high-density regions separately, separating them from low-density points, it struggles a lot in the case of clusters of similar density. The algorithm is not deterministic in the sense that it forms different clusters on different trials. The reason is that the border point that is reachable from more than one core point can join either cluster depending on the order of processing the data points. Sometimes choosing the value of epsilon can be difficult, especially when the data is in higher dimensions. And here's a Jupyter Notebook example of a demo of the DBSCAN clustering algorithm. What you're seeing here in these slides are cut and paste I did from the HTML file that was output from running the program. But I also am uploading the Jupyter Notebook for this. So if you want to go and actually execute the code to see the DBSCAN run and create the clusters, you could do that. So again, this is the code. Here we're doing the plot. And here's the final result with DBSCAN. And we have 3 clusters in purple, light brown, and light green. And you can see the noise points that are left over as the black dots. And here's a k-means, a simple Jupyter Notebook example. This is the HTML, but again, I uploaded the Jupyter notebooks or a notebook for this, so you could go and execute the code. But here we're generating the data set. And here's the final clusters, 3 clusters in k-means. So in summary of DBSCAN, DBSCAN is a widely used density-based clustering algorithm that excels at finding clusters of arbitrary shapes. Again, DBSCAN uses 2 main parameters, epsilon, or the radius from the core point, and it's a distance perimeter around a core point where border points are looked for, and minimum points, the total quantity of points in a cluster, including the core point. DBSCAN has a concept of noise, so it works well with noisy data sets. It's robust to outliers or noise points. It's implemented by many tools out there, including scikit-learn. So it's very easy to run DBSCAN if you want. DBSCAN does not require the number of clusters to be specified prior to execution. And DBSCAN also supports non-globular structures. So on the next 3 slides here, I have some internet links and links to YouTube videos I used to put this presentation together with. And 2 of the YouTube links are for the demos I showed you, and the other ones are just videos I watched to understand DBSCAN and k-means scan, clustering techniques better. And that's it. Thank you for your time. If you have any questions, please let me know. Thank you.